Good morning, everybody. It's a very good opportunity for me to express my work here. So, I'm going to describe the present status of primary frequency standard at NPL India. So, this is my outline of my talk. So, uh, NPL is one of the premier institute in India which realizes the units of physical measurements based on the international systems or SI units. And also we have at our time and frequency division there, so where we used to maintain the realize the SI seconds. So before going into further details, I just want to uh, say that in our time and frequency division there are basically three major activities. One is the fountain, another one is the time dissemination, and another one, third one is the time scale. So I am associated with the fountain activity mainly. So this the constructional details of our fountain. So this is the actual physics package of our fountain, and this is the optics setup. So this is the actual 3D geometry of our fountain. These are all the three magnetic shields, and this is the flight tube, and inside them there is a microwave cavity for interrogation. This is a mode chamber. This is a detection zone. So in detail, this one is the mode chamber with a detection zone, and basically we have started developing our fountain from 2008, and we have finished in 2011, and it's a 001 geometry. We have two anti-Helmholtz coil configuration in order to produce mode, and the rest of the details are given here. So overall vacuum for our fountain is like 6 × 10 to the minus 10 torr with two ion pumps located on the top of our fountain. Beside physics package, we have an optical setup, and we used to have two ECDL lasers, one for master and one for the repump. So, and from here we harvest our six cooling beams and detection beams. So these are the little details of our optical setup, fairly very trivial. We have the 5 AMs, among them 4 are in double pass configuration, and the FWHM of our beams are like 22 mm for 2 verticals, and the detection beams are the 15 mm FWHM, and polarization, and we transport the lights to the physics package via polarization maintaining fiber. And additionally, there we have used mechanical shutters, 5 mechanical shutters to block the laser lights to prevent light shifts. And beside the physics package and optics, we have lots of control electronics. The majors are the AM controller, the fountain sequence controller, microwave synthesizer, and the data acquisition system. So this guy basically controls all the sub processes of our entire fountain process. And we have our microwave synthesizer, which is precisely tunable for Cesium transition frequency, and we acquire or process the data via NI USB DAC card. This is actually our microwave cavity inside the flight tube with a Q factor of 2000. It's located 52.5 centimeter above the mode chamber. This is the actual image of our cloud formation and launching. We trap near about 10 to the 7 atoms, and typical temperature of after post radiation cooling is like 6.7 microkelvin. This is the Ramsey fringe with a toss height of 65.4 centimeter above the mode, and the interaction time is like 325 milliseconds with a line width of 1.54 Hz. So now come to the evaluation of fountain. So this is the typical traceability chain of our fountain. So we have only one hydrogen measure by which we used to phase compare with our fountain, and then we have the satellite links to trace to BIPM. This is in detail our frequency evaluation scheme. So this is our microwave synthesizer, which actually produces 9.192 gigahertz and transfers to the fountain physics package. And we have a hydrogen measure which is phase log to OCXO, which is further reference to this microwave synthesizer. This is the typical Allen deviation, modified Allen deviation of our fountain, and we have so far achieved 6.5 into 10 to the minus 13 for short-term stability, with typical statistical uncertainty of 1.74 into 10 to the minus 15 at 1 day averaging time. So, beside this, for our fountain, the major dominant systematics are the second order Z1 shift, black body radiation, gravitational rate shift, and the cold collision shift. In order to measure the second order Z1 shift, we have launched our atom cloud at different launch height, and we map the magnetic field inside the flight tube. So this is the location of our Ramsey cavity, and we launched up to there, and the stability is pretty good, less than 1 nanotesla during the, and we usually launch 60 in this region. So in order to measure the black body radiation shift, we have 3 calibrated platinum resistance thermistors along the flight tube, and before and after each evaluation cycle we measure the temperature of the flight tube to measure the black body radiation. And for the gravitational rate shift, we have our calibrated position of our GPS antenna, which is on the roof after each evaluation cycle, top of our laboratory, and from that reference point we have measured the microwave cavity height. It's typically near about 180 meter above the GON, and from this we used to get like 19.6 into 10 to the minus 15 bias with an uncertainty of 0.1 into 10 to the minus 15. And now I come to the cold collision shift. This is the major dominant bias of our present fountain, and unfortunately we are not able to evaluate this in proper way. So basically the major constraint for this thing is like the signal to noise ratio. Although we have a MOT, we trap a lot of atom, but due to the velocity distribution we come up with a very less number of atoms, and also we have not put any gator just after the MOT, and MOT is our detection zone is situated just above the MOT. So there is a lot of background pressure which affects actually our signal. So eventually we used to get like 0.5 volt signal over a 5 volt pedestal. So even a little change of background suffers a signal to noise very badly. So we have taken a large amount of uncertainty, around 20% of the total bias. So this is the typical uncertainty budget of our fountain. So we have not been able to measure the other biases since these are the major dominant. So we have performed the international intercomparison with other countries, and we found that our fountain frequency is pretty good. This is a typical result from the 20-day evaluation measured between PTB Germany, SU Russia, NIM China, and with us, NPL India, via two-way satellite transfer and GPS carrier phase. And once we have evaluated that our fountain frequency is more or less right in the region, so then we have run our fountain for rigorous evaluations. During May 2013 to February 2014, we have run rigorous evaluations to evaluate the fountain, and we have communicated our results to the BIPM. So this is the present status, these black dots of our fountain. And we also have recently contributed during November 2015 to BIPM with live contribution, but unfortunately since our system is aging, so it is very hard to maintain the entire fountain operation continuously, and so every other day we have faced many problems, like sometimes ago we faced major problems with our mechanical shutters. 2 of shutters broke down, so we found very hard to find the alternatives, and then we came up with some camera shutters, and they are working fine. Then after replacing them, when we have contributed to BIPM during November 2015, then our master lasers start playing, and now our fountain is not, first fountain is not presently not operational. And we are also have started our development for the second fountain, which we predict of the much better accuracy, which has a 111 geometry. This is actual the CAD drawing, and we'll implement the optical pumping to to enhance the signal to noise ratio, and also we will implement a 4-feet cavity, which is made by with the collaboration of NPL UK, and uh, Curtis here, who is actually inventor of this cavity. So this is my summary of this work. So NPL India has CSF1 has a good agreement of 10 to the minus 15, and we are now evaluating continuously the systematics. So we have contributed also live to BIPM, but this is not sufficient, and we are not able to run our first fountain, and we need a lot of development in our first fountain. So in parallel also we have started developing our second fountain, so hopefully this will be in operation within 1 year or so. So for the second fountain we have already tested all the individual vacuum parts and the electronics subsystems, and now we are integrating them, and parallelly we are also developing the optics. So these are my references, and I am very much thankful to IEEE IFCS 2016 and UFFC community to provide me the travel support, and DST India, and also authors are very much acknowledged to PTB Germany, NIST, USA, and NPL UK for their valuable suggestions and support to make this work so far. Thank you.